Hi, everyone. Thanks so much for being here. My name is Ansh Gupta. I'm a fourth-year undergraduate student at the University of Arizona, majoring in astronomy and physics. And today I'm going to be talking about the research I've done this summer as part of the University of Kansas REU program under the excellent advisorship of Dr. Allison Kirkpatrick. And my work covered the ionization conditions of galaxies from the James Webb Space Telescope. In this talk, I'm going to be showing you my evidence that galaxies with lots of high energy radiation tend to be young. They tend to be forming lots of new stars, and they tend to be disproportionately massive. And if we can find a galaxy with lots of high energy radiation that doesn't follow these trends, it can help us identify active black holes in the center of galaxies. So if you look at a galaxy through a telescope using your naked eye, most of what you see is light from stars. But galaxies are made of lots of other kinds of material. There's lots of gas and dust in a galaxy that's not associated with a star. They can form the spiral arms of some galaxies or be swirling all around them. And some of the clusters of gas that we're interested in are called H2 regions. These are big clumps of molecular hydrogen that appear as red blobs on the image here. And these are clouds that are constantly forming new young stars. And so I have an image of an H2 region here. And so in these regions, there are lots of new, young, very hot, and very massive stars being formed. These stars are pumping out huge amounts of high energy radiation, which sculpts the gas around them and ionizes it. Stripping the gas is atoms and molecules of their electrons. And so if we can find a way to identify ionization of the gas in a galaxy, it can help us trace the formation of new young stars. One way we do this is by looking at the spectra of a galaxy. And so this plot shows the amount of energy coming in at different wavelengths of light from a particular galaxy. We see two spectral lines on the right that are associated with emission from O3, doubly ionized oxygen. And this basically tells us that there's emission coming from these highly ionized elements that are associated with young stars. The spectral line on the left-hand side of the plot is called hydrogen beta. It comes from neutral hydrogen and is found in pretty much all galaxies. And so by comparing the relative strengths of these kinds of spectral lines, we can figure out how much ionization is in a particular galaxy. Now, when we do this, sometimes we find a level of ionization that's not possible to be generated simply by stars. That means there's some other source of high energy radiation. And in many galaxies, this source of radiation is an active galactic nucleus, or AGN. At the center of every galaxy is a supermassive black hole, which can be billions of times the mass of the sun. And as dust and gas fall onto this black hole, it heats up due to friction and starts glowing, and can often emit huge amounts of high energy radiation. And this is often responsible for the extra ionization we see in some galaxies. So if we see an outlier, a galaxy with lots of high energy, galaxy with high amounts of ionization, that can indicate the presence of an AGN, which are interesting objects of study in their own right. Here I have a diagram of the history of the universe. On the left-hand side, we see its earliest moments, and towards the right-hand side, we see the present. One way to contextualize the ages of galaxies is a parameter called redshift. We know that the universe is expanding, and as light leaves the galaxy and travels towards us, it's shifted towards the red part of the spectrum by this expansion. And so the galaxies that I studied have a redshift range from 2 to 8. Now, the youngest of these galaxies are present in a universe called the epoch of reionization, when the neutral hydrogen that filled all of space became ionized by high energy radiation. And so that's a third reason we're interested in studying the ionization in these galaxies, because it's currently an active area of study where the radiation that ionized this hydrogen came from. Possibly some of it came from these galaxies. It leaked out of these galaxies and ionized the hydrogen. Now, an interesting consequence of the high redshift of some of these galaxies is that spectral lines that we want to observe that might otherwise be in the visible part of the spectrum that we can see with our eyes are shifted into the infrared. And so that motivates the use of the James Webb Space Telescope, which is an excellent instrument which observes in the infrared. Specifically, the data I got is from the NIRSpec instrument, which takes high resolution spectra in the near infrared, just past the red part of the visible spectrum. And the program that my data was collected by, it was called the CEERS program. It looks at an area of the sky called the extended Groth strip, which contains around 40,000 galaxies. And it's actually located near the Big Dipper asterism. So if you're ever looking at the night sky, you can take a peek at this survey. Here's an example of some of the data from one of the galaxies that I looked at. And here are the 4 spectral lines that I used to determine the level of emission in these galaxies. We have an O2 line, a neon 3 line, an H1 line, and an O3 line. That's 4 spectral lines. And we take 2 ratios, dividing one line by the other, dividing O3 by H1 and neon 3 by O2. That gives us 2 numbers that can track the amount of ionization in a galaxy. And so then what I did is I plotted these 2 numbers against each other. And so on this plot, each axis corresponds to one of these ratios, and each point on this plot is a galaxy. And so on these plots, as a point moves up and to the right, that means the gas in each galaxy is ionized to a greater extent. And I'm going to be showing you several of these plots with the same labels. Now, for reference, the dotted black line shows the amount of ionization that we see in galaxies in the local universe. In particular, I colored this plot such that the yellower a point is, the higher redshift it is, and the bluer a point is, the lower redshift it is. So yellower galaxies are younger and bluer galaxies are older. And we see a very nice trend between the level of ionization in a galaxy and its age or redshift, which implies that younger galaxies are forming stars at a higher rate. Now, I mentioned earlier that if we find an exception and we see a level of ionization that's improbable for a galaxy, it can help us identify AGN. And we see one major exception to that trend, which I've circled there. This object has a very high level of ionization, among the highest in the sample, but it's at a relatively low redshift. And so we examined this point and we found that it actually has some X-ray emission. And by visually inspecting the spectra, we found that this point is indeed an AGN. So we looked for the exception and we found it. Now here's a similar plot where everything is the same, except I've recolored each galaxy so that the yellower points are more massive galaxies and bluer points are less massive galaxies. And we see a slightly less significant, but still a correlation between the mass of a galaxy and its level of ionization. The next thing I wanted to do was calculate the number of stars that are being formed in each of these galaxies in each year, the star formation rate. And you can do this by looking at the H alpha spectral line. Now, just purely calculating the star formation rate isn't a great way to look at galaxies because 10 stars being formed in a massive galaxy are going to have a much smaller effect than those same 10 stars being formed in a tiny dwarf galaxy. And so we want a number that can help us compare galaxies with much different masses, which is why I calculated the specific star formation rate as well. This number is the star formation rate of a galaxy divided by its mass. And so now we can actually compare how many young stars are being formed in a galaxy for its size. And I plotted this specific star formation rate against each galaxy's redshift. And I show that plot here. As you go further up on the plot, a galaxy has a higher specific star formation rate. And as a galaxy is further right on the plot, it has a higher redshift. Now, previous data has shown that most galaxies fall on the so-called main sequence. They fall on a very narrow band. And so many of the galaxies in our sample are indeed on this main sequence. But interestingly, there are several galaxies which are far above the main sequence, which implies that they're forming stars at a disproportionately high rate. And so we call these galaxies starbursting galaxies. We also see several galaxies that are below the main sequence, meaning that they're forming fewer stars than we'd otherwise expect. And we call these quenching or quenched galaxies. It's interesting the variety of objects we have in this sample. Here I show you some more of those diagrams where we plot ratios of spectral lines against each other. So again, we're back to where up and to the right on the plot, meaning the gas in the galaxy is experiencing a higher level of ionization. In this first plot, yellower galaxies have a higher star formation rate and bluer galaxies have a lower star formation rate. And we see a relatively weak trend, which makes sense because as I mentioned, the star formation rate itself is not a great apples to apples comparison. In this middle plot, I color galaxies by their specific star formation rate, where yellower galaxies have a higher specific star formation rate and bluer galaxies have a lower one. And we see a really nice trend here, which is expected. If a galaxy is forming lots of stars for its size, we expect those stars to be ionizing the medium around them. And finally, I made a third plot in which the yellower points on this plot are galaxies that are far above the main sequence, and the bluer points are galaxies below the main sequence. And we actually see a relatively weak correlation, which is surprising we should expect that galaxies above the main sequence that are starbursting, making lots of new young stars, should have lots of ionization. But that's not reflected fully in the data here. And so that might imply that there's some dust obscuration in these galaxies or other processes going on. So this is an area of further investigation. To wrap up my talk, I want you to come away with a few things. First, I showed you evidence that the ionization of many high redshift galaxies are correlated with their physical properties, like redshift, their star formation rates, and their mass. If we can find a galaxy with high ionization that doesn't follow these trends, we can identify active galactic nuclei. And investigating the ionization conditions of these galaxies can help reveal information about the reionization epoch, one of the most crucial stages of the universe's early formation. I'd like to once again acknowledge my advisor, Dr. Allison Kirkpatrick, all these fine people, and thank you all for listening.